My name is Gautam Kamath. I'm an assistant professor at the University of Waterloo. I'm going to tell you about CoinPress, Practical Private Mean and Covariance Estimation. Now the title's a little bit of a misnomer, because while we apply it to private mean and covariance estimation, what we actually present is a somewhat more general framework for private parameter estimation and confidence intervals. This is based on a joint work with Sourav Biswas, who's an undergrad here at the University of Waterloo, Yihe, who works at Microsoft, and John Ullman, who's a faculty at Northeastern University. So I'm going to start with a teaser. In one slide, I'm going to summarize what this talk is about. So we're given a dataset x1 through xn from some unknown distribution p, and the goal is to estimate mu, which is the mean of p. Classic setting, I'm sure many of you are familiar with it. But the goal is to do it privately, and we're going to use differential privacy, which I'll define in the next slides. There's a lot of new challenges that arise just due to this one keyword of privacy. The one we're going to focus on this talk is what I'm informally going to call, where does my data lie? We're going to illustrate this in a few slides from now with an example of what can go wrong under differential privacy. In this talk, we'll present a practical and general tool for private point estimation and generating private confidence intervals. It'll work not only in the univariate setting, but also the multivariate setting. Not only for mean estimation, but also covariance estimation. And while our focus is really in this talk on going beyond the theory, which we've already established in the past, and really making something which is usable and practical, we also at the same time give algorithms which match the near optimal sample complexity for private parameter estimations which have been previously established for these problems. Okay, so this is a talk on privacy, so let's talk about what the notion of privacy is. So we're going to use differential privacy, a notion introduced by Dwork, McSherry, Nassim, and Smith in 2006. So I'm first going to informally describe a type of game which characterizes what it means for an algorithm to be differentially private. So there's some algorithm or statistic M which produces an output. An output will look at this, an adversary will look at this output, and based on this output, they have to determine which of the two inputs was fed to this algorithm. Was it the dataset X shown over here? Or was it this dataset X prime, which is identical to X, except it differs in the addition of just a single individual to the dataset? So the question is, they have to determine which of these two datasets was fed into the algorithm, and they're trying to get a significant advantage over just random guessing. Essentially, what differential privacy says is, if they are unable to get a significant advantage over random guessing, then we say that the algorithm is differentially private. You can perhaps see what this means for the algorithm to be private in the sense that, if they can't even tell if you, where you is this frowny face, if you are in the data set or not, then they can't possibly infer anything about you. Good, so a little bit more mathematically, we say that an algorithm M is epsilon differentially private if for all inputs X and X prime which differ on one entry, we call these neighboring datasets, we have the following mathematical guarantee. We say for all subsets of the range that mx in S is roughly the same as mx in S in terms of probability distribution. So that's a little bit mathematical, but essentially what this says is that the probability distribution of outputs when X is fed in should be roughly the same as the probability distribution of M's outputs if X prime is fed in, where X and X prime differ on only one entry, and this holds for all possible inputs of this nature. So they have to have similar probability distributions of outputs. Now this is, we use in squiggles equals. What does this actually mean? Well, what we actually want is a multiplicative approximation, so e to the epsilon. And generally we're going to think of epsilon as being some small constant. Think about it being like 1, or maybe 0.5, or even 0.1. Anything in sort of this sort of ballpark is a reasonable privacy parameter, let's say. So we're going to want this type of multiplicative guarantee in terms of epsilon differential privacy, or otherwise known as pure differential privacy. However, we're actually going to use a slightly different notion. We're going to use something which is slightly weaker than this pure differential privacy notion. In particular, we're going to use something which I'm not even going to formally define in this talk, but something called zero concentrated differential privacy. For those experts of you in the audience, this is a notion of privacy which lies between pure differential privacy and approximate differential privacy, that is between epsilon dp and epsilon delta dp. But we're not going to go too much into the details and just say that it's a reasonable notion of privacy, which is related to pure differential privacy, which I told you. Good. So now that we have the privacy notion out of the way, let's look at the actual setup. The setup is the following. There's some unknown distribution P. Via random sampling, this generates a dataset x1 through xn, and this dataset is fed into an algorithm, or a mechanism as it's sometimes called, M. This algorithm produces an output object, y. This y has some utility which is measured with respect to the original distribution P. In particular, note that this is not with respect to the dataset x1 through xn, but with respect to the original distribution which generated the data. So we want to infer something about the distribution, not the dataset, though these sometimes might be in line with each other. And so there's two desiderata. The first one is that the classic one, we want the algorithm to be accurate. So this is a stochastic guarantee, sort of in expectation or with high probability we have that the algorithm is accurate. This may require assumptions about P to hold. For example, maybe sometimes we need that the that the distribution is Gaussian. And today, what do we mean by a utility guarantee? We put in quotes. Well, today utility means that the algorithm is going to produce, say, an estimate of the mean, and we want that this estimate of the mean, that would be mu hat, we want this to be close to mu, which is the mean of the true distribution. We want these two to be close in L2 norm. So this is the classic guarantee so far, but now additionally, we need that the algorithm is private. This is the new thing that we want, and we want it to always be private. What do I mean that we want it to always be private? Well, we want it such that for any x1 through xn, that the algorithm M is private. In particular, even if the dataset is very low probability under the distribution, or that there might be some sort of contamination parameter, then we still want it to be private. The reason is that, if we have some sort of model misspecification, which is sort of our fault, we don't want to necessarily compromise the privacy of the individuals who gave us their data so kindly. So we really want a worst case privacy guarantee here. And like I said, today we're going to want epsilon squared concentrated differential privacy. That is a type of differential privacy. And the question that's always at the back of my mind when looking at this type of question is, what is the additional cost of privacy? That is, one is sort of the classical setting, but how much more data or what more is needed in order to be able to solve 2 in addition to 1? All right, so that's the setting out of the way. Let's talk about the main challenge we're going to face today. And like I said, it's where does my data lie? Let me give you an example to show where this comes up in private data analysis. So suppose we're given a set of female heights, x1 through xn. We want to compute the average height of the distribution which generated these heights. So the population average, if that's familiar to you. And here's what a data set might look like. We have a set of heights, all listed in centimeters, and we want to compute the mean of this data set, or rather compute the mean of the underlying distribution. So non-privately, this is very easy to do. Non-privately, we know you can just take the empirical mean. Like this is something I'm sure you all know and you'll never forget. This is, tattooed on my back. But just take the empirical mean of the data set, and that's a good estimate in pretty broad settings. You don't even have to worry about where the data set is. Each individual point can be around 0, it can be around 100, it can be around 1,000,000. This will still work and give you a pretty good estimate of the mean, regardless of sort of where the data lies. However, the same is not true under differential privacy. In particular, recall that we were trying to say that, adding or removing a single point shouldn't make the statistic change much. But imagine, say, if a basketball player came along and she might be comparatively tall in this data set. So that would sort of shift the empirical mean up significantly. That would be perhaps non-private. So we have to cover for this somehow. And in particular, we're going to use basically differential privacy 101. We're going to use the Gaussian mechanism in order to sort of cover up contributions like this from a single individual. So what is the Gaussian mechanism? Well, the Gaussian mechanism says, sort of in words, that if you add noise proportional to the statistic's sensitivity, then the result will be private. So as a result, we can consider the following statistic. Mu hat is now the empirical mean, but plus some Gaussian noise. So you can see the standard deviation of this Gaussian is delta over epsilon n, where we let delta be the sensitivity of summation of xi's. That is, how much can the sum change if we change just a single data point arbitrarily? And if you think about this for a minute or two, you'll quickly realize that this is not going to be good. The reason is that this delta can actually be quite large. In particular, the sensitivity is actually unbounded for a summation, because you can just take one point to be arbitrarily large. Okay, so let's pretend we're on, say, a finite computer. Well, if you just take a float or something, then delta might be real max. You know, you set one person's height to be incredibly large, and that implies that delta can be arbitrarily large as well. So now what are we doing? We're taking this statistic and we're adding on Gaussian noise with standard deviation, which has this delta in it, which is incredibly large. As a result, this results in, us adding an inordinate amount of noise, which will completely obliterate any sort of signal that we had in the original statistic, and we will not get an accurate answer at all. So hopefully this problem is clear. The fact that, the empirical mean or other such statistics typically have rather high sensitivity, and this leads to challenges when we try to estimate them naively in a private setting. Okay, but you might be thinking, this is a silly case, right? We have heights, what's a reasonable height? A reasonable height is maybe 150, 160 centimeters. 1.8 times 10 to the 308 is not a reasonable height. Well, so this gives us a very first algorithm, essentially, which uses our prior information about the dataset. Not to be confused with a Bayesian setting, but this kind of like a priori information which we had. And this is that most females are between 120 and 200 centimeters. Most adult females will be between these heights roughly. So these are rather generous, in fact, in the sense that these will contain almost all females. But, this gives us somewhere to start. So based on this information, this tells us that, for example, a point that's that large will not be a valid point, so we can get rid of it. So perhaps formalizing this, the correct thing to do would be to, clip or Winsorize our data based on these bounds. What do I mean by this? So clipping a data point means that if it's bigger than some threshold, then we round it down to that threshold. And if it's smaller than some threshold, we round it up to that threshold. Statisticians like to call this term Winsorization. So pictorially illustrated, you can see it here. We have these purple lines, which indicate the bounds on what we sort of a priori knew about where the heights will lie. So we can clip or Winsorize it to these boundaries. Now, we can see that this has limited the sensitivity. That is, this delta parameter, the sensitivity of the sum, is now down from real max. Now it is down to just 80 because, you can take one point from the right side and move it all the way to the left side, or vice versa. This can only change the sum by at most 80. Therefore, we've already enjoyed a significant improvement, and this will give us a non-trivial algorithm for the setting. However, this isn't the end of the story. We're not going to end the talk here. I'll point out that 80 divided by epsilon n is still a large number. It's non-trivial. It's going to give some sort of significant overhead in terms of the noise we've added. And the real goal here, the question we're trying to solve here, is how can we minimize the cost due to this uncertainty? So that's the problem we're going to try to solve. And in the next slide, I'm going to tell you our solution, which is very simple, and in my mind at least, is very simple and works pretty well, it seems. So our approach will involve shrinking confidence intervals. I'm going to describe in this slide sort of the setting that we'll work in a very broad or general sense. And then we're going to specialize it to a more specific setting, say Gaussian mean estimation, in a few slides from now. But we'll keep it broad and high level just so that you can see that this is generally applicable. So we imagine that there's some data set x1 through xn, which is distributed as some distribution p, which is not known. We have the following guarantee. We have a confidence interval for the mean mu, which is has coverage 1. And we'll say that mu is going to be in minus 1, r, comma, r. So this is kind of weird. We know that the mean is between some two numbers. And why do we need that? Well, that kind of encodes our prior knowledge that we used in the previous slide, saying that we know that almost all female heights are going to be between 120 and 200 centimeters. Well, similarly, we're encoding that the mean of the distribution is going to be between these two endpoints. and that will be how we're using this prior knowledge. It turns out that this is kind of necessary in the private setting for concentrated differential privacy. Okay, so that's the first thing we need. And additionally, we need the fact that we can compute non-private confidence intervals for the distribution class P. For example, if P is a Gaussian distribution, this is something we can do no problem. We know this very well. So that's the prerequisites. Those are what we need to use this setup. And it's a very simple 3-step algorithm, essentially. The first 2 steps you already know. The first step is to Winsorize our data or clip the data set so that it's not arbitrarily large. We do this based on our prior information, confidence interval. The next thing we do is we compute a noise mean. This is done just as we showed before. But the place where we diverge from the previous strategy is in step 3. So now, based on some noise mean, we take into account the sampling error as well as the error due to the noising of the mean for privacy. And from there, we can compute a confidence interval for the mean of the distribution. Based on this, we've got a new tighter confidence interval than before, hopefully, and we can just iterate as we like. Okay, so let's demonstrate this via picture. Like the first step I showed is exactly the same as before. We Winsorize our data. This time we do it on slightly different numbers, these 2 purple lines here. From there, we compute the noise mean. So again, you can see that the true mean is going to be somewhere around 160 for this data set. But because of the noise that we have to add due to privacy, you can see that the noise mean is maybe somewhere closer to 170. Then from here, we've got this noise mean. And what we do from here is we compute a confidence interval for mu. So given this noise mean, we account for the error due to sampling and the error due to addition of privacy. And we can say, okay, for sure, the mean, or with very high probability at least, the mean will lie between these 2 new barriers. And in fact, of course, it does. From here, we've got these 2 new purple barriers. We're going to iterate the algorithm. We're going to Winsorize the data and compute a new noise mean, which we can see now after the second step is somewhat closer to the true mean. And we can just repeat, draw up new purple bars based on new confidence interval and maybe get something even more accurate and so on. Good. So that's like the idea and sort of a sketch, and that's pretty much it. Let's talk a bit more technical and get a little bit more precise for specific settings. So here's the first theorem for Gaussian mean estimation in just 1 dimension. There's a few lines to this, so let me break it down part by part. So we say that there's a data set, x1 through xn, which is generated according to some Gaussian distribution with unknown mean, but known variance. Like I said before, though, our mean is going to be bounded in absolute value by some parameter r. What we say is that there exists a private algorithm. This private algorithm will output a confidence interval, L, R for mu. So there's nothing surprising, but the sort of main meat of the theorem is in the next line. We say that if n is sufficiently large, this confidence interval has 1 minus gamma coverage, and the width is bounded above by this term up to, say, constant factors. All right, this is a lot to parse, so let's break it down a bit for you. You can see the first term here is the non-private rate. So what I mean by that is the fact that if you take a non-private Gaussian confidence interval, it'll be something of width comparable to this, essentially, up to some constant factor. And the second term can be seen as the cost of privacy. That's how much the rate will increase and how much the width of the confidence interval will increase. So we'll note that one thing, that this is a lower order term, since this is 1 over square root n, but this is 1 over n. So it should die faster, especially for large values of n. It should become negligible. The second thing is the fact that we have this new requirement here that we need n to be sufficiently large to get a reasonable accuracy estimate. And this is kind of necessary. Like, this is where dependence on r comes in. And like I said, this is necessary in the sense that where there's lower bounds which sort of say that a dependence on this will be required. So this is sort of the way a statistician might look at it. Let me give it to you for perhaps computer scientists in the audience. And this is the way I might like to think about it sometimes, which is if you want to estimate the distribution in total variation or L1 distance to accuracy alpha, you need the following sample complexity, 1 over alpha squared plus 1 over alpha epsilon plus square root log r divided by epsilon. So the first term here is the non-private sample complexity, and we can see that the other two terms are essentially the cost of privacy. All right, so that's the theorem statement. I'll leave it up for a minute for you to parse it all. And in the next slide, we're going to show what the algorithm looks like specialized to the setting. The next slide will be the most technical slide in the whole talk, so don't get too frustrated if you get a bit intimidated, or if you get a bit lost. We're going to bring it sort of a bit more down to earth afterwards. Okay, let's continue to the algorithm. So here you can see CoinPress. CoinPress stands for Confidence Interval-Based Private Estimation. Like I said, the setup is that we're going to have a data set which is generated from sub-Gaussian with unknown mean and known variance, where the mean is bounded. The first thing we're going to do is we're going to initialize this interval L comma R to be sort of the initial bounds on where we know the mean lies. The idea is that this interval L comma R will always be a confidence interval for the true mean, and we're going to start with it as wide as necessary, and then we're going to shrink it over the iterations of the algorithm until we're kind of satisfied with how narrow it is. The first step in the algorithm is the second step. The first step was really just an initialization. But anyway, this step is to, like I said, Winsorize a data set to some appropriate interval. So let's unpack what this Winsorization is, what this interval is. So essentially, we start with the interval L comma R, where we know the mean is, but then we widen this to essentially contain pretty much all of the data, in the sense that these intervals, even if the mean was at, say, R, this addition here makes it so that it's wide enough in order to hold, say, 99.9% of the data. This Z is sort of a tail bound for the Gaussian. So this means that almost all of the data will fit within this interval. In fact, in the algorithm, we set it somewhat differently, but like the idea is that, we Winsorize so that if it's truly from a Gaussian, then we don't actually touch the data and things are okay. We're just, the point of this is not to actually Winsorize, it's really just to limit the influence of outliers to the data set and the empirical mean. So now with this Winsorization, we just do essentially what we did before. That is, you define delta to be the most the summation can change with just one point being changed. And then we compute a point estimate Z, which is going to be a point estimate for the unknown mean, which is just the empirical mean after clipping and Winsorization, but noised according to Gaussian noise with a standard deviation delta over n times epsilon. So this is where the sort of first algorithm I told you ended, sort of the strawman algorithm. But it's our algorithm differs in the sense that now we generate a confidence interval around this point estimate. You see that we have Z, which is a point estimate, which is going to be the center of our confidence interval. But what we do is we widen it by these two terms here. We can say that the first term, the first widening, deals with error from sampling. So this will account for just the sampling error. We'll note that this is exactly, the Gaussian confidence interval, what you would put if you're doing this non-privately. But additionally, we have to take into account the error due to the added noise here. So essentially, if we build this confidence interval which accounts for both types of noise, then we have a sort of high probability guarantee that the true mean will lie within this interval. So that's great. We're going to let LR be the endpoints of this new interval, which will hopefully, given our parameter setting of n, will be narrower than before. And then we return to step 2, where we do the same thing again. Winsorize, noise, confidence interval. That's the whole algorithm. And after repeating this enough times, say like log of capital R iterations, that's in theory at least, in practice we can just do a few, but after several repetitions of this Winsorize, noise mean, confidence interval framework, then we can just output the confidence interval L comma R. And like I said, informally, this is a private and valid confidence interval for the mean mu. Cool. So I'll leave this algorithm up, but you can see this is the whole thing. It's very simple. It fits in like one slide, maybe just 3 lines, which are really doing all the work here. Cool. So that's great. This is an algorithm for the univariate case. let me compare with some prior work. So one of the first works in this area was that of private histograms. Sorry, before I continue, let me just mention that a lot of works didn't even focus on this problem of where the data lies, in the sense that they just assume, okay, we're going to assume that our data is bounded absolutely somehow. Don't worry too much about how that is done, or just assume somehow that's given to you. So that's sort of assuming the problem away. But there's been a few works which have explicitly tried to address this problem. The first one, which I am well aware of, is one by Karwa and Vedant. This was a very inspiring and influential paper, which takes a private histogram-based approach. So let me just describe to you their approach in sort of 2 lines. The first line is to use a private histogram method to coarsely estimate the mean. So just to try to get an estimate of the mean which is in the ballpark of the true mean. It's very sort of coarse. But then once you have this coarse estimate, which is still it's not terrible, but it's still a bit coarser than what we would like as a final point estimate. Based on that, then we just do essentially the algorithm which I presented first here. You Winsorize your data set to this coarsely estimated mean. You noise the mean, and that gives you a fine estimate of the mean. Essentially, just one round of our algorithm as we describe, no iterations. So that's one approach, which is really great. There's other approaches based on, say, quantile-based methods. This is a result of Du et al. And these are both very good for univariate Gaussians. They both beat us empirically and do really, really well for univariate Gaussians. But there are some drawbacks of this type of approach. In particular, neither of them scales very well in the multivariate setting due to issues associated with the cursive dimensionality. For example, histograms work very well in 1 dimension, but the multivariate setting, this kind of blows up with the dimensionality of the problem. Furthermore, the second approach that I mentioned here, the Du et al. Approach, it assumes symmetry of the distribution, which might be a bit limiting if we're considering other settings, other types of distributions. So there's ways of dealing with this multivariate drawback based on, say, doing it independently on each coordinate and then combining it. But as we'll see practically, that this has some significant drawbacks and will outperform it. In particular, our approach will be general and will scale easily to the multivariate setting. Cool. So let me show you the theorem for multivariate Gaussian mean estimation. We're not going to do this in as much detail as the univariate Gaussian mean estimation, in the sense that I'm just going to sort of flash the differences, but we're not going to walk through it once again. So the theorem is the following. This time we're given data from a Gaussian with unknown mean and just, say, identity covariance for simplicity. And we're told that the mean of the unknown distribution is bounded in L2 norm by some parameter R. Then there's the private algorithm, which produces a confidence ball this time. Now it's no longer an interval because we're in a multivariate setting, but there's a ball. And this confidence ball has 1 minus gamma coverage if you take enough samples, and it has a radius of bound similar to before. The main differences here are the fact that instead of now that we're in the multivariate setting, we have to throw in a D rather than it would be 1 there before. So this D really shows how we have to pay based on the dimensionality. And like I said, here's the other way of viewing it, where you do it in terms of the sample complexity in order to estimate to alpha total variation distance. You can see it's essentially what you'd expect. Again, comparing with the non-private setting, the first term is what you pay non-privately, and the second and third terms are what are incurred due to privacy, which can be a lower order term depending on the value of epsilon. Okay, so that's the theorem. Now let me show you the algorithm in one slide. It's in one picture, in fact. This essentially illustrates the same type of thing. This should be kind of intuitive to you, and if you really understood the one-dimensional case, this is essentially the same idea. First of all, you start with R1, which is a very big ball where we know the mean lies somewhere within. But our data set is within this very, very small ball right here. So what we do is take the empirical mean, do some clipping, take the noised empirical mean, and compute a confidence ball, and that will give us a significantly smaller ball, this R2 here. So repeat that again, clip, noise, the mean, and build a confidence ball, and it'll give you an even smaller ball, which you can see right here. And finally, putting a point estimate that we derive as a result of that, then this gives us an estimate of the mean, which you can see is pretty close to the true mean, which is not bad because we originally started with a lot of uncertainty in where our mean could lie. Good. And let me show you the algorithm in comparison to before. I'm going to flash it up again, but we're just going to highlight the differences with the previous one, in the sense we're going to color the differences in red. So once again, we're going to have that the mean is bounded above by r. We're going to initialize the ball to be, instead of initializing the confidence interval, we initialize the ball to be sort of where the mean lies, which we know beforehand. This time, the Winsorization is performed with respect to the ball with the, our confidence interval, but now we widen it by the radius by theta of square root d. The reason why it's a theta of square root d, you can compute it more exactly if you'd like, but I just am suppressing some of the dependencies and some of the parameters here. But we do square root d because if you know a Gaussian, most of the data lies on a very thin shell, which is square root d away from the mean. So this should contain most of the data just as before. We define the sensitivity as before. We noise the mean, the empirical mean as before, except this time we add Gaussian noise to each individual point, to each coordinate rather. And then based on this point estimate, z, which will be a point estimate of the unknown mean, then we generate a confidence ball just by building a sphere around this, just based on the confidence intervals due to the sampling error, as well as the confidence interval due to the noise addition. We let b, c, comma, r be this new ball and just sort of iterate. Once again, after several repetitions, I think this should actually be d log r, not just log r. We're going to output a confidence ball b, c, comma, r. And once again, the theorem informally is that this is a private and valid confidence ball for the unknown parameter mu. So that's it for the theory pretty much for now. Let's talk about the experiments and show you how this actually performs. I'll point out right now that all of our experiments are available publicly online. You can just check out this link and play around with the code. I'd be happy to hear any comments you might have on it. So let's take a look here. I'm going to plot, comparisons where on the x-axis we have the value of n, so that's the number of samples. On the y-axis we have the L2 error of a method. We can see there's a number of different methods we compare here. Well, some of them that we compare, first of all, the blue line is the non-private one. You can see here. We're not going to be able to do better than that. And the red one is our method. You can see a few other methods. For example, the Karwa-Vadan one is the green line here, and SimQ is the do-it-all method, which is here. That's the brown line. So you can see that our approach with t equals 2, so that's 2 iterations, actually outperforms pretty much everything else by quite a non-trivial margin. To zoom a bit more in, so this plots the L2 error, let's look at the excess L2 error. That is, how much worse than the non-private estimate are we? And you can see here that our method, t equals 2, drops fairly quickly to almost 0 error, excess error, whereas SimQ, which is the do-it-all method, which is the next best one, you can see here, there's significantly more error for all n, orders of magnitude in some cases. Cool, so that's for d equals 50 dimensions. I'll mention also that even in low dimensional settings, we also have an advantage. So here is just 2 dimensions. Like I said, in 1 dimension, Karwa-Vadan and SimQ both beat us. But in just 2 dimensions, we already see significant advantages. In particular, you can see that we're the best here. And if you just compare the excess L2 error over the non-private method, once again, you can see that we drop very quickly to almost 0. Whereas the other approaches are kind of competitive with each other. This is also true in sort of the high dimensional, or rather the multivariate setting, where the dimensionality is rather high, say 500 dimensions. You can see here, comparing ours with SimQ, well, for small n, they don't even get something which has non-trivial error. Ours looks like it's 0. It's not really 0, but there's just such a large scale that it looks like it. But let's, cancel this out. Let's look only from somewhat larger n. And you can see that even if you look after the point, it sort of drops from the stratosphere, you can see that we have significantly smaller error than the alternative. And this is the next best algorithm. We hid the other lines. As one last investigation that I'll highlight here in this talk, let me mention that we need even very minimal prior information. So a lot of people ask me, how do I set the value of t? How many iterations? How do I need to know this is converged? And kind of the punchline of our experimental results for mean estimation is that, it doesn't really matter. You don't need to know anything. Just set t, set the number of iterations rather high, and it still works very effectively. In particular, let's see here, this is a plot which on the x-axis, instead of increasing n, we're looking at now at a fixed n, but we're looking at the value of increasing r. So sort of as we go further to the right, that means that we have less and less prior information, whereas the y-axis shows how much L2 error we have. So we can see that some of the methods, such as the SimQ method of do-it-all, they immediately incur significant amounts of error as we increase our uncertainty. And naive sort of coordinate-wise methods also incur significant error. So ours seems to be advantageous there. Let's zoom in a bit. So this is, removing some of these baselines. We removed the two that went crazy before. And actually, we replaced SimQ with SimQ given twice as many samples as we had before. Why do we do this? Well, it seems like it's not really a fair comparison if it immediately gets something that's totally wrong. So let's try to give it twice as many samples as any other method and see if it performs okay, or once it gets past this initial pain, or if it's still worse. So that's why we advantaged it. We also compare with the other things. Say Carvavadana is significantly worse than our method with, say, larger t. And let's zoom in on, let's get rid of some of these earlier ones. Like, for example, t equals 2, t equals 3. They show that they cannot be effective at, say, larger values of r. So in other words, let me state that again. If we only do a few iterations, this will not give a good estimate if we have a lot of uncertainty. But it seems like what really does well when we have a lot of uncertainty is just setting t, the number of iterations, to be very, very large. So if we set, say, t to be 10, this is kind of perhaps overkill, but we see that it is effective throughout for even very large amounts of uncertainty, large r. But we don't really see any sort of disadvantage for small values of r. In particular, we kind of have to pay more privacy, or we get a weaker estimate for earlier iterations when we have large t. But you can see that even when we only have t equals 4, then there's no real noticeable error difference for small r. So we can see that, there's a non-private estimate. Our private estimate with t equals 10 is fairly close, and everything else seems to be either worse. So recall that this is SimQ even when given twice as many samples, and this is t equals 4, which is fewer iterations, and that goes bad. But so the punchline of this slide is just set your number of iterations to be rather large, and it'll be pretty good in most cases. So that's all I want to say about mean estimation. Let's talk very briefly about covariance estimation, which you have all the ideas I claim. It's more mathematically challenging, but really just the exact same ideas. We start by Windsorizing the data, we noise the empirical covariance, and then we recurse on the confidence ellipsoid that we've generated. So same ideas, harder math. The harder math involves some analysis of the spectrum of the empirical covariance matrix plus some Gaussian noise, which is a little bit more tricky whenever you're dealing with matrices and stuff, but it's not too bad. In particular, it was done in some previous work where they perform hard thresholding and rescaling of eigenvectors. I say they, it's really myself with Jerry Lee, Vikrant Singhal, and John Ullman. This appeared in Colt last year. So it's possible to really analyze this. We have to do a slightly more fine-grained analysis, the reason being that their approach is really a hard thresholding approach, which is not generally practical. And in particular, their approach has too many hyperparameters. It really was focused on, trying to get a theoretically good algorithm, but not actually a practically good algorithm. Our goal is to try to go beyond, the theoretical investigation so far and make something that's actually practical and usable. So our softening kind of helps with both of these issues. It reduces, one, with the number of parameters, hyperparameters, and two, it removes some of these pain points associated with hard thresholding. Cool. I'm not going to go through the algorithm itself, but let me show you just a picture of what it does, because here's some very nice pictures which were made by my colleague John. So imagine here's our Gaussian. It looks something like an ellipsoid in high dimensions or multi-dimensions. So this is what our Gaussian looks like, something like this. The covariance will be shaped maybe spherically or elliptically like this. And we have some uncertainty in the sense that we know our covariance is somewhere, some ellipsoid living within this much larger ball. So based on this ball, what we're going to do is we're going to clip and we're going to add noise. And this yellow circle here, estimate, represents the amount of noise that we're adding. So this is our sort of Gaussian noise. So based on the addition of these two objects, the sort of empirical covariance and the noise here, then what we get is something that looks like this, which is not quite the original covariance. You know, you can see it kind of has a bit more error in some directions, especially the short direction is kind of a little bit fatter than it should be. But what we can do based on this new covariance estimate is now we can draw a much tighter confidence ellipsoid on where the true covariance must lie. And indeed, like, you know, here's a ghost of the original covariance matrix, and you can see that it indeed lies within this confidence ellipsoid. Cool. So I could present to you some more experimental results in the setting, but instead, let me, like plots as before, but let me focus on, I think, a kind of cool application, which I think is rather promising for differentially private, exploratory data analysis. So let me tell you, first of all, about a study done by November et al., which appeared in Science in 2008, called Genes Mere Geography Within Europe. What the researchers did was they took a high-dimensional genomic dataset from a GWAS study, if you're familiar with what that is, and there's about 1,000 individuals on that order. They took each individual and colored their data point with their country of origin. For example, an individual who's from Spain would be colored blue. An individual who's from Great Britain would be colored pink, and so on. What the researchers did was the following. They took this high-dimensional genomic dataset. They did a principal component analysis and took the top two principal components. They plotted the data onto these two principal components and plotted the projection in the plane, giving rise to this picture here, which you can see fairly closely resembles the map of Europe above. So to try to interpret that a little bit less technically, what the researchers did was they found that the two directions which seem to explain most of the genetic variation correspond to the real-world directions latitude and longitude. And this results in the sort of catchphrase that they came up with, which is that genes mere geography within Europe. So this was considered to be really cool, but the thing is that I'll just comment that they used a genome-wide association study, which is a genetic data set. Genetic information is generally considered rather sensitive from a privacy standpoint, so perhaps you would want to do the same analysis privately in order to maintain privacy of the individuals who participate in it. So if you just try to use previous methods naively, then this corresponds to the t=1 case of our algorithm, and you can see here Europe is decimated. It doesn't look like anything like the previous picture. You've kind of lost all the structure in these principal components which you had before. However, if you run our algorithm with just, for example, 3 iterations, you see that it starts looking like it did before. On the other hand, and if you continue running it for, say, more iterations, say t=5 iterations, you can see this very closely resembles the original map of Europe projection, the non-private setting. I'll comment that, of course, like plotting the data points like this is not private because that reveals, each individual data point where they lied. But I will mention that actually releasing the principal components, which have a pretty strong correlation with the original principal components, that is a private operation. So you can see that doing this analysis will let you extract the sort of private structure of the data set. Okay, so just to conclude, I'll mention that we have a generic recipe for private estimation. I'll just show it right here one last time. Just use a priori knowledge to Windsorize a data set, compute and privatize a standard estimator, generate confidence intervals after accounting for this noise addition as well as noise in the data set, and then repeat. There's a very broad and generic recipe which we apply personally to mean estimation, covariance estimation, and principal component analysis, but I'm sure there's many cases you can apply this far beyond what we look at in our investigation. So with that, I'll conclude. Let me just say again that this paper is joint work with Sourav Biswas, Yihe, and John Ullman, and the code is available here at this URL. So please check it out. Check out the paper if you want to see more details, and I'm happy to answer any questions you might have. Thank you.